Every golf ball is covered in hundreds of tiny dimples. At first glance, that seems like terrible engineering. If drag slows objects down, shouldn't a perfectly smooth ball fly farther? The answer is surprisingly no. Those tiny dimples exist because they create turbulence, and under the right conditions, that turbulence helps the ball travel much farther. The goal isn't to eliminate drag completely. It's to reduce the kind of drag that has the biggest effect on the ball's flight. Imagine hitting two golf balls with the exact same club at the exact same speed. One has dimples, the other is perfectly smooth. Most people would expect the smooth ball to fly farther. Smooth shapes usually move through the air more easily. A golf ball is different because it's almost a perfect sphere. As air flows around the smooth sphere, it forms a thin layer that hugs the surface. Engineers call this the boundary layer. At first, the airflow is smooth and orderly. As it moves around the back of the ball, though, it begins to lose energy and can no longer stay attached to the surface. When that happens, the airflow breaks away and leaves behind a large pocket of swirling, low-energy air known as the wake. That wake creates a low-pressure region behind the ball, producing what's called pressure drag. For a sphere moving at golf ball speeds, pressure drag is the main force slowing the ball down. This is where the dimples do their work. Each dimple disturbs the airflow just enough to create tiny pockets of turbulence. Turbulence usually sounds like something engineers try to avoid. Airliners, race cars, and high-speed trains all rely on smooth airflow to reduce drag. A golf ball benefits from the opposite. The turbulent layer created by the dimples carries enough energy to stay attached to the surface for longer before separating. That means the wake behind the ball becomes much smaller. The dimples do increase skin friction drag slightly, but they reduce pressure drag by a much larger amount. According to educational materials from the United States Golf Association, the result is less total drag overall. The dimples don't create the airflow smoother, they make it stay attached longer, and that changes everything. A golf ball also leaves the club face with backspin. As it spins through the air, the airflow above and below the ball becomes uneven, creating a pressure difference that generates lift through the Magnus effect. The dimples don't create that lift on their own. They help the airflow remain attached to the spinning ball for longer, making the lifting force more effective and helping the ball stay in the air. Golfers began noticing this long before anyone understood the physics. During the 19th century, worn gutta percha balls often flew farther than brand new smooth ones. The roughened surface was changing the airflow, even if nobody knew why at the time. That observation eventually led to purpose-built dimple patterns instead of smooth golf balls. Today, manufacturers use computer simulations, wind tunnels, and robot testing to refine those patterns. Most modern golf balls have somewhere between 300 and 500 dimples, but there isn't the perfect number. Engineers adjust their depth, diameter, spacing, and shape to balance drag, lift, and stability. The next time you tee up a golf ball, take a closer look at its surface. Those hundreds of tiny dimples aren't there by accident. They're carefully engineered to make the airflow slightly more chaotic, so the ball can fly much farther. It feels completely backwards, because our intuition says less turbulence should always be better. For a golf ball, the opposite is true. Sometimes creating a little more turbulence is exactly what makes an object more aerodynamic. That's the weird advantage hidden in every golf ball. Subscribe for more golf science.